So yesterday we discussed an overview of immunology, trying to discuss the basics of what um, we are setting the base for the rest of the course. And key to that, we talked about some of the origin of the blood cells, which were the primary lymphoid organs, which were the secondary or peripheral lymphoid organs, and how some of the cells are able to be developed in one particular part of the lymphoid organs, then migrate to another part of the lymphoid organ. So I'll try again to present just to add on to what we discussed yesterday. So teaching objectives for of this lecture is to recognize the significance of the immune system in combating infection and disease, to distinguish between the innate and adaptive immune system, to understand the mechanisms of combating infection, to know the humoral and cellular components of the innate immune system, and to comprehend the mechanisms of action of the humoral and cellular component of the innate immune system. Those were the objectives of this class. So the innate and adaptive immune system. So as we all know, we are constantly exposed to infectious agents. However, in most cases, we are able to resist this infection. And as we discussed yesterday, it is our immune system that enables us to fight off infection. And yesterday, we also mentioned to say that the immune system is composed of two broad divisions, which were the innate or non-specific immune system and the adaptive or specific immune system. The innate immune system, as we discussed yesterday, is a first line of defense, invading most pathogens and organisms or foreign entities, while the adaptive immune system is a second line or second class defense system that offers protection against any pathogen or any organism or foreign entity that we might be exposed to. And then if any re-exposure occurs, this system of ours is able to recognize with the initially developed immunological memory and react in good time to fight off whatever infection that is there. So each of these subdivision has particular components. So as we discuss forward, you will see that the innate immune system itself is divided into several components, the cellular and humoral components. And again, the adaptive immune system is also divided into a similar structure of cellular and humoral components, as we will see in one of the figures. So in addition, the innate immune system has got the anatomical features that function as barriers to infection. So the primary purpose of the innate immune system is to provide a barrier to infection. Okay, so as much as these systems interact, these systems are quite distinct and have very, very distinct function. The interplay between these two systems is very complex and is very, very coordinated within the immune system. And we will see how all this plays out. So as we go on with the overview, we are saying that although the innate and adaptive immune system both function to perform a specific task, which is the protection against invading pathogens and prevention of primary infection, they actually differ in a number of ways. The adaptive immune system requires some time to react, while that of the immune system, of the innate immune system, is that of rapid, first-hand, and is always ready to mobilize upon any detection of infection or detection of intrusion within the body. While the adaptive immune system, like I said, is slow-acting, is specific, and only reacts when an organism induces a response. okay? And once it induces a response for the first time, we develop that immunological memory that I'll keep talking about. And then once another infection of a similar organisms occur, the immune system will now be able to react in a faster way on second infection, okay? And that is what demonstrates the concept of immunological memory, as it remembers that it has encountered a particular organism and is able to react rapidly upon subsequent exposure to that particular pathogen. So if today you were to be infected with an organism that you've never been infected before, the response of the adaptive immune system would be slow as compared to that of the innate immune system. If that organism was to reinfect you sometime later, the immune system would act in more faster way. Just like I talked about COVID yesterday, whereby on first infection, usually the infection hits you bad, as the immune system is still trying to recognize what is this particular organism that has come in. But on second infection, you actually respond better and you've got a better treatment outcome in response to that particular infection. So all the cells of the immune system have got their origin in the bone marrow. We discussed that yesterday. Okay, we discussed the origin and the development of the bone marrow cells, of the immune cells coming from the bone marrow. And we've got different lines of development. We've got the myeloid and we've got the lymphoid. So when we look at the myeloid system, we have got cells such as the neutrophils, the basophils, the eosinophils, the macrophages, and the dendritic cells coming from this lineage. And when you look at the second lineage, which is the lymphoid, this is now where we have the B lymphocytes, the T lymphocytes, the NK cells, which differentiate along distinct pathways. And we'll be able to show you some graphical presentation of this. And again, key to note is that from the same myeloid progenitor stem cells, we also have the development of the erythrocytes, the platelets, the neutrophils, the monocytes, which then develop into the macrophages, and also the dendritic cells, as I earlier mentioned. Then we also, on the other side, again, on the lymphoid side, we also give birth to the NK cells, T cells, and the B cells. So this is similar to what I just said in the first 2 points. For the T cells, which we have just mentioned, that is stem from the lymphoid lineage. If you remember yesterday, we talked about the T cell development being in the bone marrow, and then these then migrate to the thymus, which is a primary lymphoid organ. So the bone marrow and the thymus being primary lymphoid organs. Okay, so once the T cells are developed in the bone marrow, these then migrate to the thymus, where they undergo differentiation, or for lack of a better term, maturation. It is that at that point in the thymus that they are now distinct and developed into different classes of T cells. Okay, this is where we have got the CD4 receptor being activated or added on to the cells in the thymus, as well as the CD8 plus receptors being added on. And we'll have distinct type of cells being developed, such as the T helper cells. We've got the cytotoxic T cells being developed. All that is happening in the thymus. And also, in terms of the type of helper cells, we've got the T helper 1 cells coming into the fold, as well as the T helper 2 cells also being differentiated at that point in the thymus before they migrate to the secondary lymphoid organs. So that is very, very key to note the origin of these cells as they come through. As I said, everything stems from the bone marrow. From the bone marrow, we've got the myeloid lineage, and we've got the lymphoid lineage. And from the myeloid lineage, we've got the development of the neutrophils and the other cells, which I can basically just depict in this presentation, in this pictorial presentation here, in which we have the bone marrow. We have our two lines of lineage, the myeloid and the lymphoid. And from the myeloid, we have got two distinct development lines, in which we've got the erythrocyte, the platelets developing on one end, and then we've got the neutrophils, we've got the NK cell, we've got the neutrophils, we've got the eosinophils and the basophils. Then from the lymphoid side, we have got NK cells and the other cells generating from that end. So to sum it up, it looks like this. We've got the immune system, two distinct progenitor cells, myeloid and the lymphoid cells, giving a birth to this class of cells, where we are able to distinguish between the neutrophils, the basophils, the macrophages, and also on the other side, the lymphoid side, we've got the T cells, the B cells, and the NK cells. So this is a very, very important slide that we need to keep at the back of our heads as we come back later to actually now look at the specifics of each and every one of these cells and what is their role in the immune system as a pathogen, and as a pathogen invades the system. So very, very important slides. Like I said in this slide, the lines are distinct. Okay, let's never confuse this slide. We've got the myeloid system, we've got the lymphoid system, and from each system, we've got a particular class of cells developing. Okay, which translates to this, to this slide here. Okay. Yeah. So just to give us a snapshot of what we are up against. This is ideally it. So we've got the adaptive immune system, we've got the innate immune system, and the innate immune system is able to fight against entry of foreign organisms, against injury. Okay. Then we've got bacteria killing substances, starting from the mouth, where we have got amylase. They contain a particular that's a particular enzyme that is able to kill bacteria, starting from entry all the way coming to the skin, which protects us from any intrusion of any foreign entity, and also coming down to the mucosa of the membranes, through the respiratory tract all the way to the gut. Okay, yesterday we talked of the MALT being a very, very important component there in terms of barrier of entry. Okay, then on the other side, we have the adaptive immune system, which fights against specific pathogens or changed body cells. Okay, and this is ideally a defense which occurs mostly in the blood and also in the tissues. So this is a very, very important slide as well to understand and look at where these two systems interact and how they connect with each other. Okay, so as I said yesterday, the main function of the immune system is to discriminate between self and non-self. Anything that is non-self will be attacked and destroyed, and anything that is self will be preserved. And this is the point where we talked about the thymus there. As these cells mature in the thymus, as they differentiate, they're able to recognize the antigen/MSC complex, whether it is a non-self or it is a self. It is a self. It is the cells are maintained in a positive selection sense, and they're allowed to leave the thymus as they move from the cortex to the medulla and into the bloodstream. And if they are classified as reactive or T cells that are able to attack self, these undergo a negative selection sense, and then they are destroyed. And as we said yesterday, 95 of the thymocytes that come through the thymus are actually destroyed. Only 5% are able to mature and have the correct requirements that are required by the body. So it's a very, very competitive process that happens as the selection goes on in the thymus. Okay, this ability to distinguish between the self and non-self is very, very necessary to protect against invading pathogens. And one of the other components that we will talk about when we come to talk about cancer immunology is a component of malignant cells, where we've got development, where a self cell becomes detrimental to the immune system. It is identified as a self, but with an altered presentation, it is then classified for destruction by the immune system. So that is very, very important to know. Okay, since pathogens may replicate within the cells or outside the cells, different components of the immune system will be required at each particular time to detect and protect and initiate action that preserves the immune system and the health of an individual. It's therefore important to remember that when an organism does not, that when somebody is infected with an organism, it does not always mean disease. Okay, the immune system in most cases will be able to eliminate an infection even before disease occurs, even without you knowing it. Okay, even right now, you could be right now battling or having an infection which you're not even aware of, which the immune system is fighting. Okay, so infection doesn't always mean disease. Let's be aware of that. Okay, disease will, in most cases, occur in cases whereby the viral load, for example, if it's a virus, okay, becomes higher, or the titer of a particular bacteria becomes high in the system, such that the immune system is not able to cope in real time. And also depending whether the pathogen has been able to completely evade the innate system and also detected by the adaptive immune system. So all these systems come to play together for good. Okay, yeah, looking at the second last point there, we're saying that although the immune system for the most part has beneficial effects, they can be detrimental effects as well. Okay, sometimes I'll give an example of COVID. So during a COVID infection, the #1 cause of death during a COVID or a SARS-CoV-2 infection is inflammation, in which the body is put into a cytotoxic storm, in which it reacts more than it should, and then it initiates inflammation. And that inflammation, if it's excessive, the inflammation might actually lead to death of an individual. So that is an example of where inflammation becomes detrimental to the body. So inflammation is there to protect you, but however, if it's excessive, it can be detrimental to the immune system and eventually to the life of an individual. Okay, so during inflammation, which is a response to an invading organism, there may be local discomfort and collateral damage to the health of the tissue as a result of cytotoxic products produced during an immunological response. Okay, and in addition, in some immune responses actually can lead to autoimmune diseases. Okay, where the body itself starts to attack self, because these cells are either marked, opsonized, or have a receptor on the surface which is a foreign antigen, or which the body is recognizing as mutant. Okay, so once this happens, the body will then start destroying its own cells that are marked with any particular foreign or mutant, either a product or receptors. So very, very important to learn. The semi-immune system that protects us can also be detrimental to our health. Of course, all this depends on the level of antigenicity and virulence of a particular agent that attacks our body. So trying to go into specifics, we will see that the immune system itself is divided into distinct units. As we've said, the innate and the adaptive immune system. And as we said in the previous slide, each of these systems are divided into a cellular and humoral component. Okay, let's remember that each of these systems has two distinct divisions. That is the cellular and the humoral component. Very, very important. Okay, and now if we just delve in and just look at the innate immune system component of it, we will find that the innate immune system is composed of anatomical barriers, the humoral barriers, and the cellular barriers. Okay, and we'll go through each of these one by one, just giving a brief description of what it entails, what it entails. So for today, we will look at the anatomical barriers to infection, and as we go on in our preceding lectures, we will then go further and look at the humoral component and how the complement system comes into the fold and how all these cells integrate to initiate and what we call a primary immune response, which is a non-specific immune response as initiated by the innate immune system. Okay, so barriers to infection. Okay, the anatomical immune system. So the anatomical immune system consists of about 2 or 3 classifications, which we will talk about. And the first one are the mechanical factors. So the epithelial surface forms a physical barrier that is impenetrable to most infectious agents. And what is that epithelial surface we're talking about? We're talking about the skin. Okay, we're talking about your skin. Your skin is the first barrier to infection, and this falls under the mechanical barriers to invading pathogens. Okay, so any challenges with your skin or any disorientation of your skin will actually help pathogens and infectious agents to enter. For some, I don't know if some of you might be aware, there are products on the market sometimes that we apply on the skin. Some of them come in the form of lightening creams and other products that actually disturb the architecture of the skin in terms of being a first barrier to infection. And this actually allows certain pathogens to actually enter the skin. Remember that the skin itself is not 100% clean. The skin contains organisms, some of them which are beneficial in a consumeristic way, and some of them could be pathological if they actually penetrated the skin. So we need to be very much aware of that. And also the movement due to cilia also helps when you talk about the gastrointestinal tract. The movement of the cilia within the tract actually helps to clean out or remove pathogens that might have invaded our system, both in the respiratory and the gastrointestinal tract. Okay, so that flushing effect of saliva, of tears, also help prevent infection in the eyes and in the mouth. So when you look at a teardrop actually contains enzymes that are antibacterial, that prevent infection in the eyes. We've talked about amylase also containing a particular enzyme, saliva containing a particular enzyme, which is amylase, which is the first line of defense against any pathogens that might come into contact with any of our opening from the mouth and so forth. So that's also, then we talk about the mucus which is presenting. So you could view it as a pictorial presentation to say, okay, if we're going to talk about barriers of infection, let's start from all points of entries. Let's talk about the mouth. What happens in the mouth? Let's talk about the eyes. What happens in the mouth? What agent is available in the eyes, the lysosomes, in the mouth, amylase? What constitutes this particular element and how does it protect. We could go around and talk about all those entities and how they prevent entry of particular organisms. So like I said, mechanical barriers, we're talking about the skin as a first line of defense. We're talking about the mucus within our mucosal linings in our various parts of the body. We're talking about the cilia, which is aligned through the respiratory tract to the gastrointestinal tract. Okay, name it. These are mostly what we refer to as the mechanical barriers of entry of organisms. Then we also have the concept of fatty, chemical factors, which are also barriers to infection. Fatty acids in sweat, just our sweat, the sweat that we have. Some of us don't want to sweat. Okay, there are people who hate to sweat, but however, that sweating is also an immunological barrier to infection, which is an anatomical barrier to infection. The fatty acids in that sweat prevents growth of particular bacteria on the skin and prevents them to enter. We've got the lysosomes, as I said, in saliva, and the other enzymes the lysozymes in tears, and the other enzyme in saliva, and a lot of other nasal secretions and mucus secretion. All these prevent anatomical barriers as they prevent growth, and also they lead to disintegration of bacterial membranes, thus preventing infection. So the low pH of sweat and other gastric secretions also prevent growth of bacteria. As you might be aware, when we talk about reproductive health, it is very, very important that we maintain a particular pH in the reproductive areas, especially in females. Once that balance and the pH is distorted, that actually leads to a lot of infection, especially in women. This also happens in men, but however, it is more prevalent in women, where due to the use of other products, soaps, and the like, the pH of our private areas is distorted. And once this is distorted, it becomes a source of infection to the body. So very, very important to know. Then we've got, of course, the defensins, which are found in the lungs and the gastrointestinal tract. All these have got antimicrobial activity. We've got the surfactants in the lungs, which act as an opsonin, in that whatever organism that is determined to be foreign, these opsonins will coat it, more like sugar coating. And once it is coated with these opsonins, the phagocytic cells are able to identify them and then promote a state of phagocytosis, which then leads to elimination of these organisms. Then the other important one is the biological factor or biological barriers to infection. And this is the same concept I talked about when I talked about the skin, in that the skin has a particular flora of organism that can either be beneficial or non-beneficial. Okay, so the normal flora of the skin, also that of the gastrointestinal tract, that of the respiratory tract, can prevent the colonization of pathogenic bacteria by secreting toxic agents or substances that are able to lead to disintegration of bacterial cell walls. They can lead to inhibition of growth, and also they prevent bacterial cells from attaching to particular surfaces so that they do not invade our system. Very, very important to note. Okay, so we've talked mostly in this lecture, we've talked about anatomical barriers. Then in the next lecture, we'll talk about the humoral barriers to infection and the cellular barriers to infection. Then we'll also go on to talk about the phagocytosis and how the intracellular killing of organisms occur within the context of the innate immune system.